My dear students, Assalamu alaikum. So today we will discuss another different type of base catalyzed condensation reaction. The name of this reaction is Stobbe condensation. So first of all, we will discuss the reagents. What are the reagents of the Stobbe condensation? So in Stobbe condensation, the dialkyl succinate reacts with the ketone in the presence of a base to give you Stobbe condensation. So we will discuss the reagents separately. What are the dialkyl succinate? So as you know, we have a succinic acid. Succinic acid is a type of acid which have four groups and a dicarboxylic acid. So this type of acid is a succinic acid. So when you make the succinic acid ester on this side, the OH is removed and you have R. This is called alkyl succinate. And when you remove both the H groups and you make diester, then this type of ester is called dialkyl succinate. Here we have diethyl succinate. So when this diethyl succinate, or it is called dialkyl succinate, is treated with a base, the base will remove a proton from any of this carbon, because this one is also an alpha carbon, this one is also active methionine, so both these carbons are active methionine, so proton is removed from any one of these carbons. So when the proton is removed, carbanion is formed, and this carbanion then attack on the ketonic carbonyl group. This will attack on the ketonic carbonyl group, and this carbon and carbon bond is formed and negative charge goes to oxygen. This is the another form, a resonance contributing structure in which we have negative charge oxygen, but actually the reaction takes place with this carbon-carbon bond is formed. So when this carbon-carbon bond is formed, I have written this in this 6-membered ring, so you can say here a 5-membered ring is formed. So what happens, that the negative charge which comes on the oxygen, here the bond is formed between RCO and this carbon. See, this bond was formed. Now this oxygen negative charge will attack on this carbonyl carbon, which is the ester carbonyl, and negative charge goes to oxygen. And when then this negative charge comes back, the ethoxy group or ethyl group is removed, and you will have a 5-membered ring. This 5-membered ring is almost stable. So in the same reaction conditions, another base molecule is present. This base molecule will remove the proton from this carbon here, which is alpha carbon, because this ester group is present. So this carbon is actually alpha carbon, active methionine. The proton is removed from here and carbanion is formed. Now this carbanion comes here. We will have a double bond between this carbon RR containing carbon and this carboxyl containing carbon, double bond, and this negative charge goes to come back here. We have a COO negative charge here. So we have an S carboxylic group, and this compound, we can write this compound over here. So in this way, when a dialkyl succinate reacts with a ketone in the presence of a base, then this type of product is formed. This is called the Stobbe condensation, first part of the Stobbe condensation. My dear students, Assalamu alaikum. So now we'll discuss another different type of base catalyzed condensation reaction, which is called Darzens condensation reaction. So what are the reagents of Darzens condensation reactions? So in this case, the alpha haloester react with aldehyde or ketone in the presence of a base to give you an epoxide ring. You know what is epoxide ring? A ring which contains 3-membered, in which 1 member is oxygen and 2 members of carbon, is called epoxide ring. So it is somewhat different type of condensation reaction. In this case, in the presence of base and alpha haloester. Alpha haloester means alpha is present as a halocarbon in an ester, an alpha position, a halo, chloro or bromo is present. So alpha haloester will react with aldehyde and ketone in the presence of gas, in the presence of base to give you an epoxide. This is called Darzens condensation reaction. So we'll start with alpha haloester. You can see this one is an ester. So from the ester on the alpha position, when you have a chlorine, it is called alpha chloroester. So when you treat with a special type of base, the base here is a special type of base which is called potassium tertiary butoxide. You can see that this is a bulky type of base. In the CO group, we have 3 methyl groups attached. It's a potassium tertiary butoxide group with potassium salt. So why we are using this bulky type of the base? Because this base will not be used as a nucleophile. So if we use another type of base, small base, this small base becomes attached to this carbon and chlorine will be removed. So if we use small base, so nucleophilic substitution reaction will take place, chlorine will be removed and this base becomes attached and used as a nucleophile. So due to this reason, we use a bulky type, large type of special type of base so that it cannot be used as a nucleophile. It will only remove or abstract the proton and then cannot work as a nucleophile. So what happens that this base, which is a potassium tetrabutanoxide, a large base, bulky base, that base will remove a proton from alpha carbon and we will have a carbanion negative charge alpha carbon. Ion will attack on the keto group of the ketone and becomes attached to the carbonyl group, and the negative charge comes on the oxygen of the ketone. So when negative charge comes on here, this oxygen will attack on the alpha carbon, chlorine is removed and a epoxide is formed which is called a glycidic ester. This epoxide is a glycidic ester because the ester contains an ester group, this epoxide. So what happens when carbanion is formed? This carbanion become attached to the carbon group of keto. The negative charge comes on oxygen of the keto. This oxygen then attack on this carbon because a good leaving group is here. So this oxygen attack on this carbon and chloro group removed and glycidic ester is we can obtain a glycidic ester. Now this glycidic ester is stable, but in the presence of base, what happens that this glycidic ester first converted into carboxylic acid. This ester group is removed and acid is formed. And what happens that and this carboxylic group will be removed by giving CO2. A CO2 gas is removed and double bond comes on here and ring opens to give you this type of enol type function. This enol is a tautomer, so converted into a carboxylic acid. So this is the final product of the Darzens reaction. When we treat alpha haloester with any aldehyde or ketone, first an ester is formed and in the reaction conditions ester will opens and carbon dioxide is removed and you will get the carboxylic acid. So what is the benefit of doing this reaction? We will use with a 3 carbon ketone and at the end we will get 4 carbon compound. So one compound aldehyde ketone with one more carbon is obtained. So this is the end product of Darzens condensation. In this way we can add one more carbon to aldehydes or ketones.